Go for it.
Okay, so let's start with the intracellular fluid versus the extracellular fluid. So with intracellular fluid, that's going to be what's inside the cell. With your extracellular fluid, that can either be what is in your gets interstitial fluid or your plasma. It is. So there's two different types. And the main difference between your the plasma is going to be what's inside your arteries, and your blood vessels, and the interstitial fluid is going to be what's actually around your cells. And so the main difference between these two is your interstitial fluids are not going to have proteins. Your plasma is going to have proteins. It's going to have things like albumin. And then inside the cell, you're going to have protein. But in between those two, you have the interstitial fluid that has no protein. Okay, so the intracellular makes up about 2/3 of all the fluid in the water, and then your interstitial fluid and the plasma together make up 1/3 of the fluid in the water. And we're just going to show a cell. So this is the intracellular, this is the extracellular. In the cell, you're going to have more potassium. You're going to have proteins. On the outside, you're going to have a lot of sodium. You're going to have chloride. You're going to have bicarbonate. And you're also going to have more calcium outside the cell. So there's a lot of different things as far as there's a little bit of these things inside of the cell, but a whole lot on the outside. There's a little bit of this outside the cell, but a lot on the inside. And so that's going to give you the difference in the charges. But the weird thing is that the osmolarity of both are the same. It evens out.
Cool.
Okay. Any questions?
Can you go over like the difference between osmolarity and osmolality?
Okay. Yeah. So there's really not a huge difference. Osmolarity is just going to be how many particles per liter, and osmolality is going to be how many particles per kilogram. But with water, kilograms and one kilogram is about equal to 1 liter. So in the body, for what we're doing, you're pretty much going to end up with the same information. But say if you have molarity and you want to go to osmolarity, you have to consider whether something is going to break apart in water. So if you have hydrochloric acid, which is going to separate into H plus and Cl minus, if you have 2 molar hydrochloric acid, you're going to have 4 osmolar hydrochloric acid.
How come?
Because within your cell, so if you have hydrochloric acid in molarity, that's saying how many particles of HCl do you have? And you have 2. But osmolarity is counting the number of particles. So when you put HCl in water, it breaks apart into H plus and Cl minus. So with osmolarity, you're taking into account when it's breaking apart. And
So
you're counting how many individual pieces.
Gotcha. I think that makes a lot more sense. Thank you.
Okay, and then if you were going osmolality, this is how many per osmoles per liter for osmolarity. Osmolarity. if you do osmolality, it would be 4 osmoles per kilogram. Because 1 kilogram and 1 liter are equal with water.
Okay.
So I don't really know why we would do that, because I don't feel like we're going to use kilograms very often, but just for the sake of definitions.
Gotcha. Thank you. That's good.
Okay. But then, like on some molecules, say if we have glucose, glucose doesn't break apart in water. So if you have 1 molar glucose, then you also have 1 osmolar glucose. It's only the ones that break apart and dissociate that you're going to have more.
Let me write that part down. Only say it again for me.
Only molecules that dissociate will have osmolarities and molarities that are different. And it all depends. So I'll do another example in a minute. I'll let you
Only
write that
molecules
down.
that dissociate in water will have osmolarity and osmolality that are different
Osmolarity and molarity.
in molarity.
For our sake, because in the body your fluid is water that's in, osmolarity and osmolality should always be the same.
Gotcha.
Okay, so if we had 3 moles of magnesium chloride, how many osmoles would we have?
Okay. 3 moles of magnesium chloride. So it would be so your molarity, you'd have 3 particles all together, right? You have 1 magnesium and 2 chlorine. So osmoles, you would have 9.
Yes.
Yay!
So yeah, you just look at how many particles are going to come apart, and then you multiply it by however many moles you have.
Gotcha. I'm so excited. I got
Good deal.
something.
Are we good, or is there anything else with intracellular, extracellular that you're still confused? Don't know.
No, that's really good.
Okay.
That's very, very helpful. You need your own YouTube channel.
No. I don't like cameras. Okay, so now let's do active and secondary transport.
Sounds good.
Okay, so if you have active transport, what do you know about active transport? What kind of energy does it use?
It uses ATP
Okay.
to
it
push something
directly-
against a gradient.
Right. ATP is uphill. What else do you know? So it uses pumps. Anything that directly uses ATP is a pump.
So anything that directly uses ATP is a pump.
Mm-hmm. Okay. And then, what are some examples that you know of?
Sodium potassium pump
Mm-hmm.
and hydrogen pump.
Right. Is it?
or proton.
Isn't it potassium and hydrogen? I think so. But yeah, hydrogen pump. Yep. And then what's another one that will be important for us?
The calcium ATPase.
Mm-hmm. Okay. And there's also one that's active transport that is the myosin ATPase. So it can be a pump or a ATPase. Either one of those tells you that it has to be primary active transport.
Gotcha.
Okay, so if we think about active transport, your active transporters are what's going to contribute the energy for the secondary active transport. So let's take the sodium potassium ATPase for example. So you have this cell, and here's our transporter. It's going to send 3 sodiums out and 2 potassiums in. Oops, two potassiums. It's always in that ratio.
3 sodiums out, 2 potassiums in.
Right, so it's pushing both of these against their concentration gradient, making them go where they don't want to go. And it's sending out more sodium than it's bringing in potassium. So that means you already had a whole lot of sodium on the outside, and you're making even more sodium go outside. So then, are you good with this?
Yes, yes.
Okay. So because you sent all that sodium outside, you sent even more sodium outside than you brought potassium in, so it's not even. When you have a secondary active transport, you're not going to use ATP, but there's going to be a bigger gradient. The sodium's going to want in more than it did before. So no matter what, sodium is going to come in. Okay,
Mm-hmm.
so there's 2 kinds of secondary active transport. You can have co-transport or counter. If you have co-transport, that's sending 2 things same direction. With counter-transport, you're sending 2 things opposite direction. Okay, and so sodium is going with its concentration gradient, but whatever it's going to be transporting is going against. So one example of co-transport is taking glucose into the cell. So you can send the glucose against its concentration gradient, and sodium, that extra sodium with the concentration gradient, and so you can bring both into the cell at the same time.
So the glucose just kind of piggybacks off of the sodium.
Right.
Okay.
The sodium really, really wants to go. And it wants to go so bad it takes something with it.
Gotcha. Let me write that down. That was really, really good. So the sodium wants to go into the cell. Wants to go into the cell. Badly enough that it can take something with it,
Mm-hmm.
like glucose.
Yep.
Gotcha. And this is an example of co-transport, right?
Right. Because both things are going into the cell.
Same direction. Into the cell. Gotcha.
Okay. So look in your book really quick and see if you can find counter transport. What is it sending into the cell? I
Okay.
think I want to say it's calcium. It's taking back out.
Calcium, sodium. So the
Okay.
sodium's going in, calcium out.
So right, so as you can remember, there's not a lot of calcium floating around in the cell. There's a lot of calcium in the sarcoplasmic reticulum, but not just
this.
out in the cell. But there's a lot on the outside. So if you want to send the calcium out where there's a lot of calcium, you have to use the go power of the sodium coming in, and they can swap places.
So the calcium doesn't want to come out of the cell because it
Right.
doesn't have much. So it's got to have something that's going to make it go out of the cell.
Mm-hmm.
Okay. Gotcha.
And so since both of those are going in opposite directions, then it's countertransport.
Okay.
So when they say that this is active transport, you're using the gradient, the concentration gradient of the sodium to make things move one direction or the other. You're not actually using ATP anywhere, but if your ATPase quit working, you couldn't do it because there wouldn't be enough sodium on the outside for it to forcibly come in. Does that make sense?
Can you say it again? Maybe I.
Right. Okay, so when you have your ATPase, it works on the cell by forcing 3 sodiums out and taking 2 potassiums in. It's sending more sodium out than it's bringing potassium in.
Right.
So it's like you're scooting even more and more and more sodium out and making the concentration of sodium on this side way higher. And so if the concentration gradient over here was just regular, if this quit working
Mm-hmm.
and you didn't have as much sodium on the outside, then it wouldn't want to come in. If it doesn't really want to come in, it can't take these things with it.
Okay. So the primary active transport is the sodium potassium ATPase. Is that
Mhm.
right? And then the co and the counter transport, those are secondary transports to the primary sodium potassium ATPase.
Well, they're not really connected in any way.
Okay.
They're completely different.
They're just two different
Different
modes
receptors.
of active transport.
Right.
Okay.
But the sodium here, the sodium that's going in, it comes from this extra that we stuck out.
Okay.
So if we don't have this extra going out, we don't have this extra that wants to go in.
Gotcha. Okay.
And so these processes, they go on like all the time. Just constantly going.
Gotcha.
Okay? Any questions?
No, that was good.
if I have, this is my ion channel, whoops. What is a voltage gated ion channel?
That is,
What opens a voltage gated ion channel?
like it has to depolarize, right?
Right, okay. So what does it mean when something depolarizes?
It becomes more positive
Yes, or less negative.
or less negative.
So voltage gated to open needs depolarization. So an example of this would be your voltage gated sodium channels. In a neuron, once you get to a threshold, these are going to open and they're going to let sodium come into the cell. So with voltage gated ion channels, you can have gates. You can have activation gates and inactivation gates. So the thing about these gates is that both of them have to be open for the ion to actually come through.
So you can have, repeat that one more time. You can have activation gates and inactivation gates.
Right, on your voltage gated ion channels, you can have activation and inactivation gates.
Activation and inactivation gates. And both gates have to be open for the ion to pass through. So is like one of them like on this channel is one of them an activation gate and one of them an inactivation gate? Okay.
So, okay, if you have, let's say this is the activation gate. Your activation gate is going to be the one that opens when you depolarize. So, we're not depolarized, so it's shut. But your inactivation gate, it doesn't really need to be shut, so it's open, just at normal conditions.
So the activation gate needs to depolarize, is that what you said?
When you depolarize, the activation gate is going to open. So it's normally closed.
Normally closed. Okay.
Okay, so when you depolarize, or the inside of your cell gets less negative, that triggers this activation gate to open. And also tells this inactivation gate to close.
Okay.
So the depolarization tells both of them what to do. But the activation gate opens a lot faster than this one closes. So that's where you're going to get all of your sodium that rushes into the cell really fast. Because in that time lapse where this one is open and this one is like slowly closing, then the sodium's going to come through. And once this one closes, no more sodium comes in.
Okay, so it's trying to beat the light.
Right, yeah, it's trying to beat the light.
Okay.
Or if you think about like doors, some doors open really fast. like you barely touch them and they swing open. And some doors are like that little like really creepy thing, and even if you pull them, they won't come through. This is a fast door that like slams open. This is a slow door that like barely creeps closed.
Gotcha.
And the sodium comes in during the point where this one is opening and this one is closing.
Gotcha.
Okay? So that's kind of how you get your action potential to start. When you have the sodium rushing in, at the very top of the action potential, this is where this gate gets completely closed.
Okay, hang on. I'm gonna have to write all that down. So, the sodium rushing in.
Right. So this is like where the activation gate opens.
Okay.
And this stretch going up, this is where the sodium's coming in. And as the sodium comes in, the inside of the cell gets more positive because you're sending a positive ion into the cell.
Right.
But then here, you have this gate, it completely closes, it just seals off. And so you can't send any more sodium in, but you're gonna have a drop now because remember your sodium potassium ATPase that's pumping things out, it's gonna start pumping things out.
Okay.
And so you're getting rid of your sodium now. You're sending it back out into the cell.
Back into the cell. Okay.
Okay?
So the sodium rushing in, that's what starts your action potential, is that right?
Well, you have leak cells or leak channels that are, you always have like a little bit of sodium coming in, a little bit of potassium leaving,
Mm-hmm.
but you have to reach a certain level of like depolarization. And it's not a lot. It's like the difference between 70 and 60.
Okay.
But when you hit that threshold, then that's going to be when, like, it's just an all or nothing effect. As soon as you hit that magic number, all the channels open.
Okay.
Okay. You ready to move on to ligand gated?
So, I'm a little confused about the leak channels. So,
Okay.
is that something that's just completely separate from the voltage gated thing? Like, like it, that, like reaching that threshold, like that doesn't have anything to do with the voltage gated part? Or?
Not especially. The voltage gated is more like how you get the action potential to happen. But it's, so with your action potential, this is the general shape. Oops, gotta go back up. So this is resting. And your threshold is gonna be like somewhere right here. This part right here, where it's actually going up to meet the threshold, is not caused by the voltage gated. It's caused by other factors. It's caused by the leak channels. It's caused by things moving in and out, just natural kind of stuff. Or like other, like when neurons are communicating with each other, there's depolarization and it's sending stuff to the next ion. And so when it reaches there, it depends on what brain you're looking from. If you're looking at the presynaptic or the postsynaptic, it depends.
Okay.
So this could be caused, I guess, by voltage gated, but it's not going to be caused, it's going to be caused probably more by ligand gated.
Okay, so it's not like all or nothing, like it's definitely voltage gated. It could be other factors.
Right. This
Okay.
part is voltage gated,
I gotcha.
typically, or it could be ligand gated. But the thing about voltage gated is you have to have a depolarization to get them open. That's what causes them to open, not a molecule, not a like an electrical impulse. Well, I guess voltage kind of is electrical, but you know what I mean?
I
Like
do.
voltage gated has to have depolarization to get going.
To get going.
Yeah. Okay. And then you have ligand gated. So ligands are just molecules. They can be neurotransmitters, they can be neuropeptides, they can be all kinds. They can be hormones. My pen is dying. So the example of this that I'm going to give you is, remember on the motor end plate, what kind of receptors are there that take the acetylcholine? Do you remember? So nicotinic. Okay. So when you have this neuron and it's going to synapse on the motor end plate, it releases acetylcholine. Acetylcholine is your ligand. So it's going to come from right here and it's going to travel here and it's going to bind to this.
So all of these things, the neurotransmitters and the neuropeptides and hormones, they release acetylcholine, or acetylcholine is a hormone?
Acetylcholine is a neurotransmitter.
Gotcha.
It's released by the neuron. Okay, so when acetylcholine binds here, the acetylcholine doesn't actually go into the cell. The acetylcholine stays outside of the muscle. But what it does is it opens up this ion channel, which lets sodium and sodium go in and potassium come out.
Let sodium go in and potassium come out.
Yep.
Okay.
So it's not that different in theory from a voltage gated. It still is letting sodium come in, or sodium go out, sodium come in, potassium go out, things like that. It can do the same thing with calcium. Voltage gated calcium channels lets the calcium come in. But something binds to it. Something that is not that molecule, doesn't require depolarization. Something binds to it and it causes a change in this receptor. And then that opens it up. That's why it's called ligand gated.
Okay.
And then remember how we talked about acetylcholinesterase?
Mhm.
Acetylcholinesterase is kind of like a vacuum. All the acetylcholine that was released, it just comes in and it sucks it out. And when it removes this from the receptor, the ion channel closes. And then the sodium potassium can't go in and out again.
So it removes all the acetylcholine, and when it does that, the channel closes,
Mm-hmm.
and then
No more sodium coming in, potassium coming out.
okay.
Okay? Any questions?
No more flow of sodium potassium. I'm good.
Okay. And then we had one more type of receptor that we studied about. And those were second messenger. So with a second messenger, you can have a lot of different things that can come in and bind to the receptor. It's specific, but you could have a neurotransmitter combined, you could have a hormone combined, pretty much all the same things as the ligand. But what it's going to do, instead of like opening a gate on the outside, in this case at least, you're gonna have your thing combined to the receptor. That receptor is attached to a G protein. And then that G protein, for this example, is attached to phospholipase C. Okay, so this phospholipase C basically tells PIP2, which is just a molecule that you have inside the cell, to make DAG and IP3. And then this IP3 goes and binds to the ryanodine receptors on the sarcoplasmic reticulum.
Ryanodine receptors. Okay.
And opens them up, and then calcium comes out of the sarcoplasmic reticulum. So in a way, it's just kind of like a chain reaction. Have you ever seen those machines where you put a marble in the top, and then this is connected to that, and this is connected to that? This is the way I look at it, because you have this chain of things right here. It binds to a receptor, but the G protein is actually what's connected to the phospholipase C. PLC is telling this molecule, okay, I need you to break apart and make these two things. When this thing is made, it's not normally in the cell, but when it is there, it goes to the ryanodine receptor, and it says, open up, let calcium out.
Cool.
And then when this is not bound, then PLC doesn't talk to the PIP2 anymore, and then it stops.
So it's all originates from that one neurotransmitter or hormone that whatever attaches to
that receptor.
Okay.
Okay, does that make sense?
It does. Very good. Thank you.
Okay, so ion channels. Let's do action potential. Alright, first, you should tell me what you know about action potential.
Well, I'm just going to be honest with you, it's not a whole lot.
Okay. Look.
So, I know what action potential is, but
Okay, what is it?
it's but like rapid depolarization, like it's in excitable cells.
So it's in excitable cells. So that narrows us down to 2 cells. Neurons and muscles. Okay. What else?
It is how the like neurons send information.
It's communication.
It's pretty much the extent of my.
Okay. It's also all or nothing. So you either have an action potential or you don't have an action potential. It has a stereotypical size and shape. So an action potential from a certain type of cell, every action potential that it ever has is going to look the exact same. And typically, they look something like that.
Just what an EKG is.
Maybe, yeah.
So the up is the depolarization of the or the first one is the repolarization of the ventricles. Then the big part's the depolarization of ventricles, and then depolarization of the atrium.
Mm-hmm. So in an action potential, this is the depolarization.
Okay.
This is repolar. I can't write sideways.
It helps me to like link it to something you know
Yeah.
that I'm familiar with.
And then this part where it's below the normal line, this is hyperpolarization.
ST depression. Gotcha. Hyperpolarization.
And then somewhere around here is going to be threshold.
Okay.
Okay, so when you have an action potential, say this is the line, if I go to right here and I come back down, like I have a little bit of depolarization, but it doesn't hit threshold, no action potential. I can, like, no matter how big it is, until it hits right here, there's no action potential. But as soon as it hits that, you immediately have an action potential. There's no turning back.
That's what ventricular fibrillation is. VFib, like when you shock someone, because it's not reaching the threshold to depolarize to contract the ventricles.
Okay.
You can look excited too, like
no
it's.
clue.
I'm like, oh, I understand now. Okay.
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 All right. So there was something else I was gonna say. Oh, action potentials are propagated,
Propagated.
which means they start in one place, but they travel. They don't stay in the same place that they started. So in a neuron, they're gonna start here in the axon hillock. And then they travel in one direction down the axon of the neuron.
Okay.
Alright? And then the reason that it can only travel one direction is, I think you may have talked about it in class, but I don't remember, is if this is your axon, the edge of the axon, you have a positive charge. And all the rest of these are negative. This is where you've had the action potential travel to already, because it's up here in the positive. This is like negative 70, this is like in the positive, like 35, 45. So this one's positive. It's going to reach out to the next guy and make this positive. But while this one's becoming depolarized, this one is in this hyperpolarization and it's very negative. So this one turns negative again and it can only go forward.
Gotcha.
Okay, so looking at this picture, what's happening with the ions during this time is from here to here. This is caused by your sodium coming in. That's what's making you more positive.
So from threshold to
the peak.
To the peak. Okay.
Okay. And then up here at the top, this is where your inactivation gate closes. And then you start having less and less sodium in your cell. So the thing about your potassium gates is they're also open during this, but they open slower than the sodium gates. The sodium gates are fast. So they're opening at the same time, but it takes a longer time for them to get open. This part down here that you see, this is caused because the potassium gates are still open. So a lot of people say that this part is caused by the sodium gates, and then from here on is caused by potassium. But in reality, they opened at the same time. It just took this long for the potassium to get fully open.
Mm-hmm.
And it just so happens that it coincides when the sodium completely closes off. And so that's why you have the dramatic decrease.
Okay.
So potassium's still open, you're still decreasing because it's sending the positive charge out. And then it keeps sending it out, and then it's like, oh wait, I got too negative. I'm gonna stop. And then you go back to normal.
Okay.
Okay. I think that's it. Is that good?
That's great.
Okay.
Excellent.